so that we don't miss. Okay, once again, hello and welcome to the Statistical Methods for Data Scientist course. So this is the week 1 we are traveling with, and my name is Mustafa Sheikh, and I'm going to be one of the tutors for this course. So we will start our lecture now. And before I start, just give you a kind of update of our a schedule of lectures and what's going to happen in these online collaborative sessions. So there are 4 tutors, as you know, from this forum. So Glenn is going to take care of all the clarifications regarding assignments and assessments. So any doubt or any confusion, any guideline, that should be given by him. So if you have any confusion, that should be directed to him, basically so that you get a uniform message instead of getting the words from different tutors. So we get one point of communication regarding the assessment related doubts and confusions guidelines. So that's Glenn. Then myself, Mustafa, and Jilani is going to take the online collaborations that is going to unfold the contents of the weeks. So what we are trying to do, we will walk you through the contents in details. But particularly, I will give some more extra on that, which is probably not covered on the text of the lesson notes. So I'll try to give something, some extra. Yes, and I'll make the slides available for you to download. So as soon after the lecture, I will put it onto the forum so that you can download, and you can also listen to the recorded audio and video. And also, we will accompany our a theory that we are going to cover on this on the lecture with solid R programming. So both Jilani and my content may be some overlapping, but we will try to make you guys more interested with picking up different examples, different problem scenario, so that you solve the same theory, applying different data set, different techniques. So that will be the approach. And yes, and we'll be keeping an eye on the forum. So if you have questions, doubts, that will be answered. Yes, I think, is everybody okay with the audio? Because I see one complaint. If not, I can't have anything. Okay, is it good? Same? Okay. Oh, good. So probably check your speaker session, and probably it's probably a problem with your end. Hopefully it should be okay. Okay, good. Thanks for all thumbs up, guys. Okay, now just going the agenda for tonight. Since it's the first lecture of myself, and I see a lot of new faces because I have been traveling with the Master of Data Science stream with other cohort. So I know most quite a few students throughout the other courses, but I see a lot of new faces in this cohort, which that's why once again my extended welcome to them. And I see quite a few known names. I can see some of them here as well. So, so that's why I just put my brief intro. So that, because hopefully we'll have some journey together with other courses like I have done with data science, which is what's the data mining, then advanced statistics, then foundation of data science, and then some of the data visualization. So these are the different courses I have already gone through with the other cohort. So, and then I will put some pick about the discussion forum we are having, and then I'll walk you through the week 1 content in detail, so that this is a quick recap of your week 1 content, which is mainly on experimental design. So about me, I'm located in Sydney, and I have a good I have done my PhD in artificial intelligence. My area of research was like a natural language processing. Specifically, I was modeling sentiment from text, so people can understand. So from a machine perspective, a machine will be able to understand the emotion, not only the sentiment, which is the negative and positive, but also in detail emotion, fear, anger, disgust, that kind of labeled emotion from the text. And yes, and as a career, so I started my career as a lecturer. Then I worked both in academia and industry. Started as a like a software engineer, and then worked to develop many systems as an engineering development, specifically all related to the web. So I'm quite familiar with many web frameworks to develop a full stack application development. Then I changed my career, like I just because you see these days there is no many system developments. So the from a career point of view, that's the good choice you have guys you have made to be a data scientist, because now we have tons of systems, and the systems are producing humongous data. Now we are sitting with tons of data and trying to decipher what's the gold nugget inside the data. And that's why if you see the job trend in Seek or any and overall, there are many jobs which is not system engineers or developer, but and a data analyst, data engineer, data scientist, so called, you can say. So that's why the problem of this area of this information is now to make a like a decision oriented data oriented decision, or like as a evidence based decision, something like that. So we have tons of data from the system, and now we are to make our decisions not whimsically, but what the previous data set is showing in terms of trending, in terms of forecasting, or even grouping, clustering, whatnot. So we can see the pattern and make a like informed decision. So that's why data science course is very important, and that's the career record. A career track record should be like, if you are system engineer, if you are in programming for a long time, you know the how the data is prepared, how the data is coming, what's the flaw in the data. So now it's a good career jump to be a data scientist, or at least data analyst or data engineer. So I will give you a career guideline in other course, like what's the data scientist look like, what should be the skill sets, and how the career like it can be progressed. But since this is a foundation type of course, which is the statistics for data science, so I assure that you are on the right track, and that should be the starting point to start your career as a data scientist. So as an hobby, I was talking myself, I do enjoy like swimming, reading, cooking, traveling, and some meditation. So hopefully you guys also share your like in the whole week your hobbies and your neck. So that's good. So we try to get to know each other, and my email address is also shared there. So if you have any questions, which could be, generally we prefer to ask the questions in the forum. But if you need any doubt that if you don't want to ask in the forum, you can you can send me email. I am quite comfortable replying email as well. So that's me. And now our lecture for also something about the forum. What I would like to say, like since you guys, some of the students, they are very new and they are not familiar or quite accustomed to the forum communication. For them, I would like to see, request them to see the guideline provided by Glenn. He has put some general guideline and etiquettes to post contents in the forum, reply in the forum. So instead of creating a new thread, if you want to reply to it sometimes, so don't create a new thread, just reply on the thread so that it keeps keep a history or keep on trailing on that. And also, if you want to create a new thread, check whether that same problem has been discussed before or not. Otherwise, yeah, just keep on adding, and in some cases just try to have a caption, some keywords, so that if there's too many contents, we can search, and anyone can search and can go to that point straight away as a keyword. So that's general, but I've seen nothing much happening on the forum. Hopefully, in the subsequent weeks, you will have more problems, like more questions, not problems, to ask, and the tutors are there to help you out. Now, about the slide. So probably you're wondering, what is this, right? So if you guys have done data visualization, and I try to make a data visualization of all the statistical contents in one page. So this is just my version of giving you a statistics, a brief story of a statistics, like what is the statistics all about, and what are the different components of it, and where it starts, where it goes, what it can do, and what are the components of it. Okay, so don't be scared. Like this is basically a synopsis of all the contents that we're going to cover through this, and probably in the advanced statistics. So if you can see, I have put the very bottom is a machine learning, a classification and prediction, just an example of machine learning use case. So this is the ultimate our approach. So whatever we are doing through statistics or statistical modeling, our ultimate approach is to go machine learning space. Okay, so machine learning doesn't work in isolation. It just rely on our data and your pattern and your like inferences, assumptions. So so it definitely is the, so statistics is the the other components that actually put machine learning into practice. Okay, so machine learning is our ultimate, but it starts from the, if you look at the top left corner, we start with this, like our, from where our data comes. So if you look at our population, what does that mean? I can like take it like probably an hour to discuss the whole slide, but I will be brief so that I can cover the rest of the slides, just to give you a synopsis of that. So population is the place, like if you consider all the data, for example, if you want to survey all the people in your town, that becomes as a population. And then the study you are doing through that population statistics is census. Like we have on Australian Census Day, the government used to go every door and get data from everyone, either online survey or like a door-to-door knocking survey. So they try to get every data from everyone. Now, if you take, because it's cumbersome, if you take a sample of the population, that's called sample statistics. So, and selecting of sample, there are different techniques. There are two techniques, random sampling or simple random sampling. So random sampling is just a version of random sampling. There is no guarantee that the same person will not be selected twice. Okay, but simple random sampling is just you take it like totally anonymous, like you give it randomly, put a number, and then you take arbitrarily a number of people from the samples, from the population. So this is basically a more robust kind of sampling, which is simple robust sampling. Now, once we have the, like we got hold of some kind of like a small, like a, not data set, like know where our study area, like our fix or target area, then we think about what we can do as a problem. So if we are looking for a problem space to solve a problem, looking into the population, probably we know that population may have a specific issues or a specific trait or specific condition. Then we will not be able to survey each and everyone. So we take a sample of it, and through random sampling, simple random sampling, we select a subset of the people or subset of the cases from the population to target a specific problem. So you know the problem space, you know what problem you are after. To address the problem, you need to collect data, and the whole process of collecting data is your study design. Okay. So we'll talk about study design. There are different kinds of study design you can make, and there is a difference between a study design and a study method. Okay, so a study method is how you solve your like how you implement your study design, like what kind of a study you want to make, and then what kind of methodology, like you are going to survey through online paper. Like these are the implementation method and approach you'll do when you implement a study design. So we do different kind of a study design that I will come later. I will explain later. So on the experimental phase, like on the study design, what it produces a kind of data. So data, once you are creating a study design, you think what kind of data you are collecting. So you should be aware of like the types of data. How many, like what are the categorical, like you probably know what is the categorical data, what's the numerical data. The data we can collect through numerical values, like numbers, is numerical, which is a quantitative data. So we can get a number of quantity value, and we know there is no quantity we can assign to the sum of the variables we have. These are called categorical, and there are two types of categorical data. You can say the ordered and unordered. That you can have a natural order. For example, the blood group doesn't have any natural order, but if you think about a Likert scale, agree to disagree, strongly agree to strongly agree to strongly disagree, they can have intermediate like different scales, which is a kind of a natural order. So these are they're not numerical, but we say these are kind of categorical data. But for even statistical cases, you will see in R, we have to convert this categorical data to some kind of number system with levels. So yeah, so because as you know, computer cannot understand the text, it has to be converted to like a number, and there are certain mechanisms to differentiate categorical data with the numerical data, but eventually all are numbers to the computer. So we know our different kinds of variables, you know that. So if we are targeting the whole population, then from these variables, if we try to calculate a measure, that measure is called parameter. If the if the measure is related to a population, that is a parameter. If the measure, for example, mean, is calculated over the population, then it is a parameter. Otherwise, it's a statistics. So we get basically we are getting a value, which is the statistics from the data set. So we know some data is there. Now is the next step. We can do two kinds of treatment on the data. One is the summary statistics, another is inferential statistics. So summary statistics give you basically the numerical like measures. For example, mean, median, mode, standard deviation, the distribution, that kind of like statistical figures, statistical measures you get through the summary statistics. So once and the data, when we try to interpret the data in a meaningful way, then it becomes information. So we are trying to apply this kind of different techniques to get insight from the data to make meaningful information extracted out of this data. So summary statistics give us one kind of information. For example, information about the data is the mean or the average, or how the distribution look like. So that kind of information we get from summary statistics. So inferential statistics give us a different information, like a hypothesis. Like if you think how significant that these two groups, the male and female, for example, differ on a particular issue. So that, and you find there are some differences, but inferential statistics give you a confidence. Like I am confident, 90% confidence or 95% confident that this is the truth. Okay, and this hypothesis testing will be learning that probably from week 3 and subsequent weeks. So you will know more about inferential statistics. If to delve into that, there are many kind of statistical tests or measures we have. So I have put that into different colors. So we have a parametric test and non-parametric test. So you know the parametric test means if your population parameter is known, for example, a parameter like the measure of mean or standard deviation is known, so we apply a certain kind of test. If the population parameter is not known, we call that non-parametric test. So same thing like goes with the categorical data or numerical data. So if our data is numerical, we probably do like a t-test. If our data is not numerical, which is a categorical data, we actually go for like a chi-square test, something like that. So I put some test names so that that names becomes familiar to you, because we will be doing this kind of test, the theory behind it, and also the R implementation of those algorithms or the statistics into a specific problem with R. So we do different tests, but before we do that, we have some assumptions of some distribution. So if the data is normal or not normal, that has to be tested, and that's what we call that's why we discuss about different kind of distribution. So the distributions comes from like either a frequency distribution or probability distribution. So if you see if we get a value like a variable, and we plot the variable and see from where the values are coming. We try to assume the value of the independent variables from a distribution, which is either a frequency or probability distribution, and we see test whether the distribution is a normal, because if the distribution is normal, then we have one kind of test. Our life becomes easier in most of the cases. But if data is not normal, we try to fit it into normal cases by data transformation. So, and all these things, like these techniques that I have summarized here, we will probably have like a review through the rest of the weeks. Okay. So I just give you like a synopsis of like a statistic on page. Now, a bit more details about those components. So, as I told that these are the different kinds of data. You can see we have like a numerical data. You can also invert because there's like a dotted arrow. So sometimes you can categorize your data, numerical data, to a category, because if you have a range arrangement, then for example, this range to this range, you want to categorize to low, medium, high, something. That's why you sometimes can convert from numerical to the category. But other examples are very simple, and in your lecture note, you have that. So you have nominal and ordinal data, and knowing those data category, it is because that actually guides what kind of test we are going to do. So if you know the data types, then it will guide the test we will be doing. And also in your capstone project and in all the projects that you'll be doing for the data science, this data category is very important to know, and you have to like indicate that in your reports. Like I have these many variables, like in our data set is like a tabular shape. We have a table, and each table represent like all the samples, and the columns represent the variables, and each column should represent one of the type of the variables, and you specify the type so that yeah, the tutor can easily understand like what are the different types of variables you are dealing. So that's your that's why you need to know what specific variable belongs to which specific category. So, and from there, not only this, but I can also have some kind of derived data, like percentages. It comes from numerical, and then you can also the ratios. You can get the rates or even scores. So these are specifically like our software or whichever tools you use that can help you to derive a variable using these using our like a given variables. So so we can create new variables and new data given our data set. Now this has because you also there is a lecture, there is like a content in your slide which is about visualization. So that's why I put a summary slide about data visualization, and probably this is familiar to you if you have done data visualizations. So from there, you know that visualization has a specific purpose from the Gestalt theory. You need to be aware like what kind of visualization is appropriate for what kind of communication you want to make. So for example, if you want to communicate a comparison type a message to your user, you can pick those kind of visualization histogram like a column chart, and yeah. So and if you are trying to see a trend line or a distribution type, then you probably see the line graph or the scatter chart. So and the composition is best for the pie chart, or probably like waterfall or even histogram could work. And then relationship, of course, the bubble or the scatter plot. So based on the purpose and the data types and the number of data points X and Y or Z, like different kinds of the dimensions, you have to pick up your charts. Just let me have a quick look into the chat. Is there anything happening over there? And okay, I'll look. I will come back to this question answer at the end. Random sampling. Different sampling methods such as stratified. Yes, I think yeah, there are different kinds of methods stratified. So we will cover that into the lecture. Yes, I will send the slide in PDF after the lecture, so don't worry about that. It will be there for you. So, okay, now what is the file? Okay, so this one. Now, probably the previous slide gave you the idea of the visualization. So just you can keep it for your reference. What kind of visualization, what kind of purpose? Because this is for like your exploratory data analysis. Like if you have been given a data set, visualization does our exploratory data analysis. It just gives you like a point of interest. Given like a random variables, and you put it into the graph and see is there any correlation, or is there any like a trend specific thing that you can like notice from this, and then you can formulate a question or hypothesis question that you can probably test with the inferential statistics. So visualization actually plays a key role before you dive into a deeper analysis of anything or any question. So so visual analytics are like a visual exploration give you that kind of like a leverage, that kind of initial thoughts to where to look at. So and it is very basically using tools is very easy. You just plot these different variables and see the patterns, correlations, or any relation, and then probably that's give you a more like a food for thoughts to choose the right questions for your hypothesis testing. So, so I recommend for your any project, always try to do visual exploration first with different tools that you imagine that might be the case, and then probably formulate your question and validate that hypothesis, or answer the question through the data. So now from the lecture notes, so we have different techniques to get an average. So the term average is a like English term, but in a statistical term, we calculate average through different measurements like mean, median, mode, geometric mean, weighted mean, trimmed mean. So you probably know all of that. I don't need to explain the formula. So basically, I put the advantages and disadvantages for you so that you can see what is the benefit of it, and why it is not good in many cases. Probably geometric mean is new to you. It's not in the slide. It's just geometric mean is you just multiply all the numbers and then root of that number of observations. So if there are 3 numbers, then we do the cube root. If there are 5 numbers, then we multiply all the 5 numbers, and the 5th root of that number becomes the geometric mean. And weighted mean is probably you can, yes, I think so. It's for the skewed data. Yeah, it is a good measure to do that. So why do we use transformation on a data set if it's not? Let me read it. Normal distributed. Yeah. So our objective is to normalize the data. To somehow we try to make the data normal. If there is no luck to translate the data to be a normal, then we have some other test to carry on. So because as I said, if data is normal, then with a lot of statistical analysis and statistical interpretation become very easier for us. But if we cannot convert that data to be normal with any kind of transformation, there are testers with non-normal data. So there are a few things that we'll do that. We will see in our programming and also in theory, see when the data is not normal, like it's skewed in any way we cannot transform. So definitely we have different statistical tests to do that. And same like hypothesis testing could be done when data is not normal. But in every possible way, we try to make the data normal, because our explanation becomes easier if the data is normal. Why do you need to normalize the data? Yeah, yes, I just answered that. Because we make our life easier, so that many statistical tests becomes we can easily apply those statistical tests. Okay, so that we can interpret the result well. And okay, so I'll go to the next ones, which is spread. Uh, Again, this is like a generic term. So we calculate a spread, and there are many measures for a spread, which is a range, which the max min, and then we have percentile, which is like or the first quartile, then 25th percentile is equivalent, and the third quartile is equivalent to 75th percentile. So, and that 5.6, like 5-point data, like we use in box plot. So that the quartile really helps to understand that box plot. And the variance is which is basically the average. You can see this an average of the squared differences from the mean. So you can see the x bar is the mean, and it's the difference, and then you get the average of that. And because if it's n-1, because it's a sample variance, but if you are trying to get a population variance, then it is n, where n is the degree of freedom. So in this case of population, we have only n-1, and I will explain that why n-1 in the next slide. And then standard deviation is just the square root of the variance, and the important statistical measure in this case is also COV, coefficient of variance, which is the percentage value of the standard deviation divided by mean. So this gives us the covariance measure from the spread of the data. Now, in a theoretical perspective, this is the basically normalization. So that probably give you some idea. If we somehow can transform our data to fit a distribution like this, as a bell-shaped distribution, then we can then it's in the parametric statistics, we can calculate the mean and the standard deviation or variance. And then we will probably see how percentage wise how many values within the range or off the range from the mean, and it becomes more explainable for us. So that's why we try to convert this data to a normal shape distribution, so that this kind of measurements can be well explained. So this gives you an idea, like we can achieve different kind of normal distribution based on different values of the sigma in the left slide. And the right slide is giving you that 68, 95, 99% rule, which is telling like where the concentration of the data, like if it is I thought 68% data is one standard deviation range, then this is the red area. If it is like a standard deviation, like 1.96, like 95% data, there's to a standard deviation range, then that's the like a formula, that's the distribution look like. So that's the once we plot the data, that's how we try to understand the distribution of the data. So here comes probably the central limit theorem, which basically tries to guess a few things. Like I give an example, like so that you can understand the concept better. So imagine if we have, for example, 120 students in our population. So there are like this class, probably 120 students. But from simple random sample, we took first 40 samples from this 120 population. And we got average, for example, average weight of those 40 students from the sample. We got one weight, for example, like 65 kilo, for example. Then we take another random sampling of the 120. We get another 40 samples, like a second sample. and then we got a average, like in the first case, if it's the x1 bar, we got x1 bar equals to say 65 kilo. And then second sample, x2 bar, we get probably 70 kilo. Okay. Then another sample we take, like x3 equals to, and that's like a 69 kilo. So now if we get, we can take as many as samples, and if we keep on doing and try to get these like a distribution of this x bar, although the individual values may not be random, may not be like a normal, but thing is that if we try to keep on this kind of a distribution, and if we do it repeatedly many times and try to put the distribution on and try to get a curve for the x bar, it will be like a normal shaped curve. And that's interesting because, and this is coming from the central limit theorem, because now if we get the x bar, and we'll be able to see the confidence, how confident are the values between from our like a simple random sample is representing the whole population. And there comes our standard mean of error, like is it like the error mean is bigger or higher, and that give us a confidence level, like okay, with some confidence we say our sample mean represents the population mean. Okay. And because because we are not calculating the whole population mean, but we are taking a random sample of the population and trying to guesstimate or estimate the parameter of that population. So there will be a difference, and the difference is basically the standard error. Okay. So to minimize the standard error, we take multiple samples, and or we can increase the sample size. So there are different techniques so that we can better estimates. So that's the different talks, but central limit theorem is giving you an idea, like is the distribution is normal, and it has like and based on the value, based on your population characteristics, you can fit into the 90, 68, 95, or 99% rule, where it like after you fit the data, you can see where your most of the data falls. So just an idea about giving you the kind of a normality and normal distribution. But if the data is not normal, then it may appear like that. So there are different other distributions, like chi-square distribution, which is not normal. And then we have like a t-distribution, which is also not normal distribution. So, but still, we cannot, because we cannot convert this data to a normal distribution like. So we have different statistical tests. So that can be applied for this kind of distribution. We have Poisson distribution that can then we apply different kind of statistical test to distribution. So thing is that once we have a data set, we know what distribution it represents, and based on the distribution, if not normal, we try to convert it to the normal. And if we fail to test the normality, and if we fail to convert the data to be normal, then we do other tests. Okay, as simple as that. So it's just a kind of if-else kind of logic, you can say. Try to be normal. If not, yeah, try to transform it to normal. If not, then we try other probabilistic measures to treatment on the data which is not normal. Now, as I said, like if in many cases we will not be able to probably transform the the data, which the independent variable as a normal distribution. So then we have to try the kind of transformations. So Y transformation is giving you the answer. So a variable may not be normally distributed in the first place, so we try to do that. Or even some cases, like in the case of linear regression that we'll be learning in the last week, if the variables are linearly related, then we try to separate that. And because there is an assumption that in the regression analysis, the data has to be linear. And if they are not linear, and we think that they are interrelated, then we have to transform that one of the variables to normal characteristics. And then in the test of spread, which is the unpaired t-test, if we try to convert that to normal. So these are the scenarios where we try to fit the data to be normal. And how we do that? there are different functional transformations. So you can do the log y transformation, we can do the square root, or we can do reciprocal, which is the one divided by the independent of the observation, and all the square, or even which is a logistic regression, like a logistic function. So this is like a logistic function, which is the p is the probability of happening, and 1 minus p is not happening, and then take the log of that, which is a kind of log out. So and that's the kind of logistic function. And once we do the regression, probably I'll explain more on the logistic function if time permits. So these are the different functions we have that we try to fit into the data, and then see visually whether the data appears normal or not. So this is the mechanism how we can check the normality. There are two ways we can check the normality of the data exists or not. Obviously, the visual inspection, which is the QQ plot or the dot plot, histogram or stem leaf plot, even box plot can give you the spread and also the outliers. So from the subjective analysis, you can see whether the data is normal or not normal. But there is certain statistical test, like my personal preference is a Shapiro test, which is SW, or you can use a KS test. So these are the two statistical tests that given the independent variable as a parameter, and it gives you like a score of normality, and basically a hypothesis testing as well. So, and then we can reject the hypothesis based on the test result, whether data is not normal or normal or non-normal. So that's more objective oriented test. So I'll explain that in the R programming session. Now, some statistical jargons probably, because your week 1 content give you some kind of statistical terms so that you become familiar with that. For example, one of them is a confidence interval. So a confidence interval is what? It's just giving a kind of a confidence level or kind of a confidence boundary, we can say. So to what confidence boundary you are saying that your sample statistics, basically you are dealing with a sample, the sample statistic of the sample, the value, for example, x mean, will represent the real mean or the population mean. This is basically an indicator of your confidence, like how confident you are to tell that your sample is representing population, and what is the variance, like what is the difference. Like, so this confidence interval is giving you that kind of a measure. And degree of freedom is one. It's like if I give this example, it will be clear. So if there are 7 hats to wear in 7 days, how many choices you can make? So you can make basically 6 choices, because the last one, last day you don't have any choice. So, and because you have to have that one, but gradually. But if you have 7 hats, then there are 6 degrees of freedoms. So in a sample, if you have n populations, and if you have n many samples from the random sampling, so we have n minus 1 degree of freedom. That means this many ways we can different choices we can have. So that's why it's the n minus 1 is the degree of freedom given a number of sample or cases is n. So this is then some other term will come up. Okay, so before we reveal more contents, like more statistical terms, which is coming next, I would like to give you kind of a explain on the study design, because your project is you'll be doing experimental design, so not experimental, your study design, and then you will be doing a capstone report on the design you will make, or probably you can take a new data set there. So the objective of a study design is to create your own data set, right? And how we want to create that, what kind of study design you want to make. So this is like a synopsis. This is a kind of a guideline I just prepared for you, and I'm going to explain that. So what are the different types of a study you can make? So these are the name. Cross-sectional study is basically study in time, like right at the moment, what is happening. So if you want to look at your class or look at on a specific like a group of people or group of phenomena you want to observe, then that becomes your cross-sectional study. So you take that point in time data and collect the information, and how you collect the information, that is basically study method. So whether you are going to interview them and record their voice and then decode this information as a text, or then do like, or you want to going to make a survey form, or you are just not just you want to observe from the from a bird, like how that behave, and then report write your own findings. So there are different kinds of method you can apply to get data explicitly or implicitly from your study, from your design of the study. So so the cross-sectional study is giving you the just in point, just give a snapshot at the moment what is happening, and you just capture the data. And repeated, like a cross study, like if you want to do kind of changes over time, you want to make like what was happened last month and this month and the previous 3 months. So you have to do the same studies, same cross-sectional study for a repeated time or repeated intervals. That becomes your repeated cross-sectional study. And cohort study is basically you get a cohort, and then it's basically a longitudinal study. So difference between cross-sectional and longitudinal: cross-sectional is just in point, like just at the moment, but longitudinal is basically more like prospective, like it's a longer time. So you just see the responses, like how it changes, how it evolves, and how it takes effects. So probably experimental is a longitudinal, because you set up your experiment. For example, you want to observe, so you created a system, and you want to see how people are behaving, how people are reacting, how the performance is doing with the system. So you create an experimental model, you involve your participants to do certain things, and you observe that, you collect data, and then it probably, and you get the data. So this is the whole point. So from each study design, you apply different methods, and then the end result of this thing is like a table of data with specific columns, and each row indicates your observational point. For example, if you are trying to say number of birds in my area, probably you can think about observing. And then you see, you can observe in different times, even you can segment in the study into different zone, which is basically our blocking. So you can create different blocks of a study area, and then a different observational time. And then you can apply different. You can ask people how many birds you see, or you can yourself engage into the observation. So that's the method, basically, how you get the data from the design. So I think you got the idea. So think about your study. Think about your study experiment, study design. Should it be like a experimental base, or like a cross-sectional study, so that you can observe, or you can fill up a survey form, and then and think about different mechanism how you can collect data from this. So and once you are designing this, thinking about the study design, there are a few factors which is coming the next. Confounding. Think about what are the is there any confounding variable? So you know what is confounding, like it's basically giving a kind of you are thinking about measuring something, but you there's a hidden variable which may affect your original finding, but you didn't thought about that affecting variable. So that is basically, for example, in the case of if you are trying to get the heart relationship between the physical inactivity and heart disease, but you never consider age as a factor of the people you're getting data from. So age definitely is a confounding variable, because with age these things may differ, or there's a relationship between these things with respect to age. So if there are some cases, for example, in your study, if you think that the number of something is increasing or decreasing, but what are the environment, what is the factor that may be affecting? So you can then think about that factor, and you can then group them. So to avoid confounding, you can have a subgroup in the you can take the consideration of the confounding variable as your as a grouping variable, and then you create your data set based on that. So don't overlook your confounding variable and mention that in your report. So yeah, experimental, and then and if you are going for experimental design, like which is involving experiment, like you are giving some stimulus and getting some responses. So in that case, you definitely have a control group which is not receiving the treatment, like a placebo, or like but they are still as if they are receiving treatment, but they are not getting the stimulus, the right stimulus. But definitely you have two groups, which is experimental group, another is the control group, and so that you can compare and contrast your result based on these experiment, like which is receiving treatment and other group not receiving treatment. But yeah, but as a placebo, they are getting some treatment but not the real stimulus. So you can then compare whether this new input of the stimulus you are providing to your experiment group is making an effect or not. So, so these are the things like a theory or kind of a common sense related to study design. So randomization is just in effect to, you can see that to avoid bias, to reduce the bias, we randomize this, and that's why simple random sampling comes into the picture. And obviously bias, is the difference between our study and the true, because it's an error basically, and a standard error is a kind of bias. So we'll never be able to accurately estimate the population statistics. That's why there will be always a difference between a population statistics and sample statistics. So that's why we try to limit, reduce the bias, so that we can obviously with some degree of confidence, we say our population, our sample statistics represents the population statistics, our population characteristics. And for experimental design, you also think about blinding of your features, like blinding, and there is a concept of double blinding, which is in the case of specifically in the medical cases, and they don't know, even the tester on the subject doesn't know which is a placebo and which is a real stimulus. So this is blinded in two folds. Obviously the group doesn't know which is who is who it is like a experiment control group and which is an experimental group. So this is randomized, and then stimulus and placebo also randomized and blinded. So blinding means totally making it anonymous, so you can't identify during the experiment, but obviously you know back mechanism, then you to collect the data, you know which is what at the end. And then to reduce the sampling error, because we always get some sampling errors from our experimental from our study. So reduce the sampling error. There are certain techniques which I have listed, extracted from your lecture note. For example, minimize the potential of bias in the selection of the sample through random sampling. So do the simple random sampling. That is one of the, and take multiple measures, which is, for example, you can take multiple random samples to better represent the population. And then use probably the larger the sample size is always give you a good result. And then avoid pseudo replication. So instead of then measuring the same sample again and again, take a different random samples from the same population. So that's why you can do, this is one of the way you can avoid the pseudo replication. So don't measure the same sample again and again. This is pseudo replication. And then minimize the effect of potentially confounding variables. So give like a multiple thoughts, second thoughts, third thoughts about the patterns of your data, like why there is some variance, or there are some like a discrepancy. If you think, is there any confounding variable that is behind the scene? If that case, identify that, and then probably subgroup that your observations, subgroup of your observation based on the confounding variable. Then yeah, these are the some terms about your statistical like a study design. You know what is balancing, so you get a right like a balance. Like if you have two groups, each group should have the same treatments, like the same number of treatments, same number of experimental elements, both control and experimental, so that your experiment is balanced. And blocking, as I said, like if you think that there could be some characteristics that actually differ your different observation. In the case of bird example, so you can see if you're thinking about like a bird, like you see some of the birds are number is higher, basically because if there is food source near the scenario, there will be bird, and there are no food source. And if there's an urban area and the rural area, so these you can then segment your area space into different, so that you know you have some expectation on those blocks, and that should be identified irrespective. If you don't have, like, you think the whole study area is one block, and when you see different characteristics and different data set, so that means your study is flawed. Basically, you have already a bias on your data, and you didn't do that, you didn't fill that, because you have considered everything as one block. So blocking is one of the techniques. You can reduce bias, because you know there is bias based on certain parameter and conditions of your experimental place, and you identify that and then block them into different groups. So and the covariates I mentioned before. You know what the covariance means. Like if there are if one increases, another increases, if there is relationship, and that could affect your response, then yeah, you just measure that as well. And skewness, you can, once you have the data in hand, then you can plot the data, independent data, the independent variables of the responses, and see is it left skewed or right skewed, and based on the skewness, or even you can do the objective test, like a Shapiro test, to get the hypothesis test for skewness, and then you do transformation. Like if it is different, if the data is too high, then probably log transformation would help. And then yeah, you apply different kind of transformations. That's the way. And you can also do a normalization, like you can take the mean, and you can deduct the mean from the samples, and then divide it by. So you can normalize the data, so that if the data use range, you can normalize the data. Just the transformation is one thing, normalization is another thing. Okay, so you transform the data to fit into a normal distribution, but normalize, you can apply the data to the like a scale, like you can scale the data through normalization. Then z-score is a measure which is giving you a kind of value to see the it's just as I said in the slide, they give you an absolute value that tells you how many standard deviations you are away from the mean. So this is kind of a measure, like how efficiently you have calculated your like a standard deviation from the samples, and then and estimating the population parameter. So z-score is a measure that's give you a kind of a measure to tell the deviation, like how your samples are deviating from the real populations, from the real scenario. And I already talked about the standard error of mean, and that's give you a kind of idea how much differentiating from the population. And if you plot that on a normal distribution, that how much values are covered under that area of the normality curve. If you, and I showed you like 90% or 97% or 68% where that belongs to. So that's give you an idea where your data is mostly fitted. So we are nearly end. So I'm not going to talk about R tonight. The tutor tomorrow is going to take you through on installing R, or any problem with the environment in R, because our programming language choice is R, the Visual Studio, R Studio. So so Jilani will spend some time to show how to download RStudio and how to configure RStudio, and probably the interface, how it works. And he will of course cover these materials of the week 1, so that you get a different interpretation of the course materials. And next week we will be also I will also do R of our so my lecture will be theory first, and then reveal those theory into practice with different data set using R, simple R programming. So if you guys are not familiar with R at all, like any programming language at all, that's why I have an intention to cover R as a programming language, just so take you through teaching a programming language. For example, if you don't have any programming language background, or you may have one programming language, probably C++ or C or even Fortran, whatever programming language you have you have learned before, we'll try to map those concepts. For example, how the controller structure looks like in R, how the variable declaration and assignment works in R, how the looping structure works in R, what are the different loops we have in R. So I will go through that level of details in R as a programming language. Okay, so that, and then in the subsequent weeks I will just reveal those contents and implement those in R. So the what I'm talking about is the next week. Yes, is the next week I will talk about the programming language R. But tomorrow the tutor is going to show you how to install R and RStudio and set you up, so that you don't get like a lag behind, or you don't get any problem. Run your first program in R when we'll be doing our R sessions from now on. Okay, so yeah. So that's the idea. So it's in the next slides and the next lecture, I will do R programming, so and also the theory of each and every week we have. So as you can see, our plan for week 2 is focus on R programming, and then next week theory of probability. So we'll talk about probability and how to calculate different kind of probability, conditional probability, okay, then the multiplicative nature of probability, and then combinations, and then implement those in R as a programming as a programming point of view. Okay, and then we will do hypothesis testing when the parametric testing, like our data is normal and we know the parameters, so we will do inference and hypothesis testing with the parameter based, like parametric test. And then week 5 will be non-parametric test, which are data we don't know the parameter probably, and also data normal, not normal. So in that scenario, we'll do some other tests. We'll get into that. And then last week will be a regression. And I think Glenn has already explained to you the objective of the assignments that you will be doing. And so as I said, like any question related to assignments, he should answer in his session. So keep those things focused to Glenn if you want to do any clarification on the assignment or any doubt there. But in our sessions, we will be basically focusing on the theory and programming and R. So thank you guys, and I will upload my lecture slides soon, and then you will be able to download. And if you have any questions, any comments, then yeah, please put it onto the forum. And that's it for tonight. Yes, thank you. And I just stop the recording now, and you will be able to download it. Okay, where is the